today's video, we will be covering the first half of Chapter 17, where we will discuss aromatic compounds. An aromatic compound are arenes that include benzene and benzene derivatives, and a little bit further in the slide discussion, we'll go through the actual properties and qualifications of what is aromatic. But to start with, it's going to include all benzene rings, so six-membered rings that have six electrons in p orbitals, three pi bonds, and their derivatives. But there's also additional compounds that we'll consider aromatic compounds, and we'll go into those in a little more depth. The name aromatic also relates to some of the derivatives that were originally isolated from fragrant oils, but there are also many aromatic compounds that are odorless. So there is some correlation to the smell or the aroma, but the actual class of compounds includes many, many more compounds than those that just have these odors. And the aromatic rings are featured in many biological systems as well as drugs. They're a source of this kind of hydrophobic electron pocket on the aromatic ring. The aromatic ring is kind of a donut of electrons, which we'll talk about. So it's really common in a lot of natural products and biological motifs. For example, the drug Lipitor contains three benzene rings, three aromatic rings, and there are quite a few other drugs that have aromatic rings. Would say it's more common than not to find an aromatic ring in a drug compound. Aromatic rings can also be fused together. So, for example, in this molecule, we have, like in this orange box, it's 1, 2, 3, 4, 5, 6 aromatic rings all fused together. And so this entire system would be considered an aromatic system. And these are all, notice all of these double bonds are also conjugated. So all of the p orbitals in this aromatic fused ring are conjugated. And so all of these electrons are kind of part of this one continuous circuit of electron density in this conjugated aromatic system. When we name aromatic rings, we're going to be naming off of benzene as the general parent name. So a six-membered ring with three pi bonds is benzene, and the common name for the derivatives will be benzene derivatives. So for example, we have chlorobenzene, nitrobenzene, ethylbenzene. And so for all of the common functional groups, we actually have common names. Um, for the most part, you'll refer to these molecules by their common name, so you should learn all of these common names. Benzene with one methyl group would be toluene, and as you can see, I'm not going to list off every single one of these, but every functional group has a specific common name that the benzene ring with that functional group attached to will be referred to as. But we also have the IUPAC name, so we can go through our naming uh, system for that. We'll be using the benzene as the parent chain if it is longer than the other parent chain. So for example, here we have a phenyl group, which is 6 carbons, and we have heptane, which is 7 carbons. So heptane would take priority on the naming. So this would be one phenylheptane because the 7 carbon heptane chain is longer. If this was something like pentane, then it would be we would be using the benzene ring as the parent chain. We can represent the benzene ring as just a pH if it is a naked benzene ring with no substituents, and this is just a shortened notation that makes it a little bit easier to draw out large structures that include benzene rings. There's a few more common names for the methyl, the dimethyl substituted benzene rings. These are called xylenes. They're often often available as a mixture of ortho, meta, or para, but we can isolate them as their individual xylenes and the substituent placement. So ortho is the location. So if we compare two substituents on a benzene ring, we'll call this methyl group in position 1 for now. Then anytime you have a substituent that's in position 2, we could refer to that substituent as being ortho to the other substituent. Meta would be 2 carbons away, so 1,3 relationship. 1,3-dimethylbenzene would be meta. So anytime you have two substituents that are 2 carbons away from each other, that would be a meta relationship. And then finally, para uh, is the 1,4 relationship. So OMP, OMP, orthometapara. And this is how we'll be using this nomenclature for not only naming, but also when we're discussing molecules, when we're discussing doing reactions, or if we're in synthesis, etc. The orthometapara is used to describe the relationship between two positions on a benzene ring. So it's important to learn this nomenclature. In this case, we have some mixed benzene rings that have two different substituents. And so this is an anisole, but in the ortho position, we have a nitro. So this would be 2-nitroanisole. Here we have a toluene, and in the meta position of the toluene, we have a bromine. So this would be metabromotoluene. And we can also name these using the numbering system. So this would be 2-nitro, and this would be 3-bromo. But the meta orthometa para relationship is also usable, and I would actually prefer the orthometa para because we'll be using it quite often when we're discussing these molecules. So naming scheme for benzene derivatives is going to be very similar to the naming scheme we've seen for other molecules. First, we'll start by identifying the parent chain. Then we identify and name the substituents. Then we number the parent chain and assign a location to each substituent. And then finally, we can list everything out in alphabetical order. In this slide, I showed with 8 different common names for these benzene derivatives. These common names are what we can use as our parent chain. So for example, in this molecule, our parent chain, well, we have a benzene as our parent, but it's a substituted benzene. So our parent here will be a phenol. And then in the 1, 2, 3, 4, and 5 positions, we have the bromines. Or this would be, they're both in the meta position. So we could call this 3,5-dibromophenol after we've numbered, and since we have the two of the same substituents, we don't have to really worry about ordering them alphabetically at all. So here's a few molecules that you can try for practice, and we'll go over the answer of these during. Let's take a look at the structure of the benzene ring for a little bit. In 1866, it was proposed that the benzene ring was comprised of alternating single and double bonds, and that this was in an equilibrium process. And this is kind of what, one of the first mentions of resonance. And so we can draw two resonance contributor of benzene, where the double bonds alternate between the two, but it's also often designated as just a ring. So in order to avoid having to draw the two resonance structures, you can draw kind of a circle of electrons around the entire ring. And this is more in tune with what the actual electron density is, which is a hybrid of the two resonance contributors, right? And so in this benzene ring, we have basically a flat disk. You can picture it like a frisbee of that's where the nucleus of the atoms are on the frisbee. And then if you took two donuts, put one of them above the frisbee and one of them below the frisbee, that's where the actual electron density resides in the molecule. And we'll talk about this a little bit more when we look at the molecular orbitals. Benzene rings are unique in that they have extremely high stability for the atom configuration compared to something like an alkene. So if we look at an alkene reaction, we did a whole chapter where alkenes are undergoing elimination reactions and addition reactions, and they can readily undergo an addition reaction. But if you use the same conditions and subject an aromatic ring to that, they will not undergo the reaction. And that's because the aromatic ring is much more stable than just a regular alkene, individual alkene. And we can quantify this stability with the heats of hydrogenation. So 120 kilojoules per molar released from an alkene, a diene 232, and with the same trend we would expect a benzene ring to release somewhere around 360, but the actual observed heats of hydrogenation is only 208, so it's actually even less than a diene. And so that's kind of the quantification of this extra stability that benzene rings have, this thermodynamic stability. We can use molecular orbital theory to help us explain some of this increased thermodynamic stability that's found in the benzene ring. We're going to use the 6 atomic orbitals, the 6p orbitals, to make 6 new molecular orbitals. And of those 6 molecular orbitals, we will have 3 bonding molecular orbitals that will be filled with the 6 electrons of the pi ring. And we can kind of look at the structure of these 3 molecular orbitals and the position of the nodes in these molecular orbitals to kind of visualize where we would expect the electron density to be found. We find that we can delocalize all 6 of these electrons in the 3 bonding molecular orbitals, and since the electron density is delocalized over all 6 atoms and over a large area, um, we're able to account for some of that extra stability that we see in benzene relative to the single and double bond counterparts. So I alluded to in the beginning of the lecture that not all of the aromatic compounds were encapsulated by just saying benzene derivatives, and that's what we're going to talk about a little bit more here. So not all fully conjugated rings are aromatic rings. And we're going to look at examples of aromatic compounds and non-aromatic compounds. So cyclobutadiene and cyclooctatriene are both rings, and they both have fully conjugated systems. But these two compounds are not aromatic. These will both act like normal alkenes would act. We can do an addition reaction to cyclooctatriene, for example, and cyclobutadiene will dimerize to form cyclooctatriene. So these two compounds are actually quite reactive compared to a benzene ring. And so there is a rule that we can follow to determine if a compound is aromatic. And this rule has 2 criteria to it. The first is that it must be a fully conjugated ring with overlapping p orbitals. The second is Huckel's rule, and that's an odd number of electron pairs, or it must follow the pattern 4n plus 2, where n equals 0, 1, 2, 3, and 4. So cyclobutadiene, in this case, has 4 electrons, so it would not follow Huckel's rule. Cyclooctatriene with 8 electrons would also not follow Huckel's rule. And we can explain Huckel's rule using the MO theory. Since we have 4 electrons in cyclobutadiene, we'll have 2 electrons that are found in non-bonding orbitals and 2 electrons that are found in the bonding molecular orbital. So since we have a closed shell electron configuration and that's unstable, it lacks a closed shell electron configuration, then we're going to have an anti-aromatic compound. When we do the molecular orbital analysis for cyclooctatriene, we see also here that we have two electrons in non-bonding orbitals, not bonding orbitals, and so we also have anti-aromatic compound. So these structures will actually adopt the cyclooctatriene will will adopt a tub-shaped conformation so that it can avoid being anti-aromatic. So we would actually call this non-aromatic. So it's not conjugated because the p orbitals are not overlapped since it has this tub-shaped conformation. We have a tool that we can use to make easier the identification of a compound's aromaticity, and these are called frost circles. The first step of the frost circle is to draw a circle, and then inside that circle we inscribe a polygon. The polygon should represent the shape of the ring that we're determining if it's aromatic or anti-aromatic. We want to make sure that at the bottom of the ring we have a connecting point. Then we can draw a horizontal line at each point of the intersection and then a line through the center of the circle. After this, we can identify all the bonding molecular orbitals, which would be below the line, the non-bonding molecular orbitals, which would be on the line, and the antibonding molecular orbitals, which would be above the line. We see for a four-membered ring that we have one bonding molecular orbital. For a five-membered ring, we have three. For a six-membered ring, we have three. For a seven-membered ring, we have three. For an eight-membered ring, we have three. Once we get up to a nine-membered ring and 10, we have five. So the number of bonding orbitals is always an odd number, and aromatic compounds will always have an odd number of electron pairs. So just to kind of summarize some of these criteria, an aromatic compound must fulfill two criteria. It must be a fully conjugated ring with overlapping p orbitals, and it must follow Huckel's rule. Anti-aromatic compounds also must fulfill two criteria. It must be a fully conjugated ring with overlapping p orbitals, and it must be the opposite of Huckel's rule. So if it has an even number of electron pairs, it'll be anti-aromatic. If the compound fails criteria number 1 in either of these cases, it doesn't matter how many electron pairs. If it's not fully conjugated ring or the p orbitals don't overlap, then it's non-aromatic. So we have three classifications for all of these molecules: aromatic, anti-aromatic, and non-aromatic. We have some rings that are fully conjugated, that are even larger than just a benzene ring. And so here are some examples of annulins. Annulins are rings that are fully conjugated but are much larger, and they can be aromatic, anti-aromatic, or non-aromatic depending on the conformation in space, the three-dimensional conformation. That'll help to determine if there's p orbital overlap as well as the number of electrons present. Aromatic rings can also contain carbocations and carbanions. We need to have all these p orbitals overlap, but they don't necessarily have to be lone pair. They don't necessarily have to be pi electrons. They can also be lone pairs. We need to have 6 pi electrons present in order to be aromatic. In this five-membered ring, we could have 4 electrons that are coming from pi bonds and also 2 electrons that are coming from a lone pair. For example, the cyclopentadiene anion is aromatic because it follows all the criteria. 1, it's a conjugated system. It has 5 p orbitals that are all conjugated. And then 2, we have a total of 6 electrons, and we can draw out all these resonance structures to kind of show that the electrons can be delocalized onto any of the carbons. So we can take cyclopentadiene and deprotonate it, and we see that it's actually incredibly acidic for a sp3 carbon hydrogen. And this acidity is attributed to the fact that the conjugate base is aromatic now. So if there's a way to go to aromatic, it's going to be a favorable path for a molecule to take. This is also seen in the keto-enol tautomerization. If we have a seven-membered ring, right, if we had 14 electrons in the system, we would say that's not aromatic. But what we could have, or if we had 12 electrons or 3 pi bonds, then we would have one carbon that's not sp2 hybridized. But instead, what we could have is a tropylium cation. So if we replace one of these, if we deprotonate, remove hydride from one of these positions, the resulting molecule here is going to have a p orbital that's empty and 6 electrons. So this would also be an aromatic species. Follows all of our rules.